Good morning, ladies and gentlemen. Welcome to the 28th International Workshop on Frontiers of Computer Vision in Hiroshima, Japan. I'm Kavita, one of the organizing member of this conference, working as Assistant Professor, School of Information and Data Sciences at Nagasaki University. As a part of our conference meeting, I would like to welcome our General Chair, Professor Takio Kurita, and also it's my great privilege to introduce him. Professor Takio Kurita received Doctor of Engineering degree from the University of Tsukuba in 1993. He joined the Electrochemical Laboratory National Institute of Advanced Industrial Science and Technology in 1991. From 1992 to 1991, he was a visiting research scientist at Institute for Information Technology, National Research Council, Canada. From 2001 to 2009, he was the Deputy Director of Neuroscience Research Institute in AIST. Also, he was a professor at Graduate School of Systems and Information Engineering, University of Tsukuba, from 2002 to 2009. He's currently working as a professor in the field of pattern recognition and machine learning in Graduate School of Advanced Science and Engineering at Hiroshima University. His research interests include statistical pattern recognition and its applications to image recognition. And he is a member of several academic societies. And I welcome our eminent Professor Takio Kurita with a big round of applause. Please, Kurita-sensei, please.
Thank you for the long introduction. I didn't expect such an introduction, but first, I'd like to welcome you all and thank you everyone for attending IW-FCV 2022. Unfortunately, due to the COVID-19, we had to hold this workshop virtually again. The FCV workshop is originally initiated from the regional friendship between Korea and Japan in computer vision and image processing. The first workshop was held in 1995. So this is the 28th workshop. Recently, research on deep learning has been advancing and the application field of computer vision has been expanding rapidly. This workshop has an important role to give their first international presentation opportunity for young researchers who are just starting their research in this field. This time, we received many submissions of high-quality research results. Number of submissions is 63. From these submissions, we accepted 56 papers with 30 oral presentations and 26 poster presentations. In addition to these presentations, we have keynote lectures by Professor Kang Byung-jo from University of Ulsan, Korea, and Mr. Hideki Aso from National Institute of Advanced Industrial Science and Technology, Japan. IW-FCV is the 28th anniversary of FCV activities. We have held the international workshop for 28 years. This is because distinguished researchers have significantly contributed to FCV activities. Therefore, the steering committee has decided to give the FCV Honorable Contribution Award to thank them as much as possible. We will announce the recipient in the award ceremony. Also, we decided to increase the number of recipients of the research awards. We will give Best Paper Awards, Best Student Paper Awards, and Best Presentation Awards. Especially for the Best Presentation Awards, we will select the best presenter in each session based on the chair's recommendation. Finally, we want to express our gratitude to all the authors and the session chairs. We also thank the members of the organizing committee, especially to the program chair, Professor Sumi and Professor Na and Professor Kaneko. In addition, we thank the local chair, Professor Miyao and Professor Aizawa. They make the online virtual conference possible. We hope you will have a great time at IW-FCV 2022. Please enjoy the workshop. I'd like to start the workshop. The next keynote lecture will start from 10 a.m. So please wait until 10.
Kurita Sensei,
はい。
is it going well?
I cannot catch.
今、麻生先生の発表は、
はい。いや、始めます。
はい。
I'd like to start the keynote lecture. At first, I'd like to introduce Mr. Hideki Aso. He is currently invited senior researcher, AI Research Center, National Institute of Advanced Industrial Science and Technology, Japan. He was a former deputy director of AI Research Center at AIST. I think we can hear the current situation in AI research in Japan, especially for the industrial application. But the title of his lecture looks more advanced or abstract. The title is the co-evolution of human intelligence and artificial intelligence. Please start the keynote lecture. 麻生さん、お願いします。
So thank you very much for introduction. Can you hear me?
Yes.
Yes.
Okay,
Of course.
thanks. And I'm Hideki Aso, a senior invited researcher of AI Center in IST. And it's a great honor for me to be here today. It's my great pleasure, and I thank Professor Kurita and all other organizers for kind invitation. So today, I'd like to talk about not industrial-oriented research, but very basic research titled Co-Evolution of Human Intelligence and Artificial Intelligence in the Real World. So I've been conducting machine learning research, machine learning related research from 1980s for understanding principles of information processing in our brain and also constructing intelligent systems, which can learn through interactions with the real world, including humans. And I've authored some Japanese textbooks of machine learning and neural networks. So currently, I belong to AIRC. AIRC is established in May 2015 and located at waterfront of Tokyo. It's one of the largest public AI research center in Japan, focusing on the industrial applications of AI, actually. And ARC is collaborating other research centers of IST and Japanese universities and Japanese private companies and overseas research institutes, and for serving as an open innovation hub for accelerating AI transformation of our society. Today, first, I'd like to introduce some recent research activities in in and around AIRC. So that are not my own research, but research done in AIRC. And then I'd like to talk future direction of AI research briefly. So as you know, wait a moment. So AI was empowered by big data from internet services so far, and it made a very great success in this area. But however, we think that AI will be installed or applied to real-world services also for realizing Society 5.0. This is our Japanese government advocating. It's a digital transformation of or AI transformation of society. Hence, we ARC are focusing on human-centered AI collaboration. AI, human-centered AI research, which can collaborate with humans in the real world. So in the course of our research on the real-world AI, we identified 3 key issues of AI embedded in the real world. The first one is engineerable. Engineerable is not maybe not correct English word, but easy to build AI. And the second one is cooperative AI, cooperative with can cooperate with humans. And third one is dependable AI. And today, I'd like to talk the first 2 of them. So I'll start from the engineerable, easy to build AI in the real world. So one of the biggest problem of AI installing in real world services using real world data is a high cost of data acquisition. So hence we need AI that can learn from small amount of data. And transfer learning is a promising approach, as you know. So as shown in this picture, current AI depends on general purpose pre-trained models trained with a large-scale data set on large-scale computing resources. Then we fine-tune the pre-trained model to various downstream applications. So this is an example of a research done in RC in a medical image diagnosis area. Here we introduced a multi-step transfer learning for medical image diagnosis. The target application is anomaly detection of bladder endoscopy image data. It's a kind of endoscopy, but available data is so small. So we first trained the model with an ImageNet large data set, and then fine-tuned the model with a gastroscope image. This is also the medical image and more available than bladder endoscopy. Then we fine-tune again with bladder endoscopy data to get the last model and achieve the performance improvement in the target task. But constructing a pre-trained model with large-scale data needs large computing resources, large computational power. So hence, we constructed a cloud system for machine learning. We call ABCI, AI Bridging Cloud Infrastructure. This is a hardware of ABCI. So it uses a water cooling system. And the system has over 5,000 high-performance GPUs and also large data storage. And in addition to the usual cloud computing service, we are promoting a grand challenge using the full power of ABCI. So we provide 24 hours of full power of ABCI without charge for the selected research teams. And this chart shows one example result of a grand challenge in 2018. In the grand challenge, it's a team of Sony and ICE conducted experiment of fast ImageNet learning and achieved a world record at that time. But not only the computing power, but the more important or more hard problem is preparing the large-scale training data. So ImageNet is often used for pre-training of neural networks like CNN. But as you know, there are several problems such as mistaken labels or privacy violated or ethics related images are included. So we propose a formula-driven data generation for large-scale pre-training. As shown in this figure, we generate fractal images using a formula of a fractal system. And we can also set label for the image by setting some parameter in this mathematical formula of fractal. Then we can use the generated fractal image with class label for pre-training of CNN and fine-tune the pre-trained model to other image recognition tasks. And the performance is, we confirm that the performance is comparable to the conventional pre-trained model with ImageNet. This is a fractal, using fractal database, and this is ImageNet. We also apply the framework to a vision transformer architecture and get a very similar result. And this work is presented at AAAI this year. And we extend to video recognition task also. So we trained a 3D CNN for video recognition, video action recognition, using video paralleling noise. This is generated artificial data, time series data. And after that, for us, some earthquake. Anyway, after that, we use kinetic data set for the second stage pre-training, and then we fine-tune the pre-trained model with other action recognition data set to evaluate the performance. we confirm that spatiotemporal initialization with a VPN, video pairing noise dataset, outperformed the previous initialization method with a deflated 3D component using 2D image dataset. So another approach for creating large dataset is a meta 3D, a meta video dataset. So these are examples of training data for action recognition. So they are pairs of short video, 5 minutes, 5 seconds or so, and action class labels. So and we already have several large-scale datasets for action recognition. However, they use different action labels each other. So hence, a researcher of Chiba Institute of Technology collaborating with AIRC constructed a meta video dataset. They gave 4 kinds of relation labels between action labels of each different datasets. So equal relation, similar relation, either relation, and no relation. So they are noted very many relation labels. And this picture shows some example of some part of the graph of action labels. So each color and shape correspond to action label in some dataset, for example, kinetics or ActivityNet. And STEA action is also created by the Chiba Institute of Technology, STEA Lab. And the link represents a relationship between the action label. So you can see some clusters in the data set also. So then you can use a multiple data set as a unified data set for pre-training. So it's an idea of a meta video data set. And you can use download the annotation labels from the homepage of the Chiba Institute of Technology, STEA Lab. Not only the visual data, but also we are constructing pre-trained model for various modalities of data, such as sound in everyday life or scientific articles. And we use a pre-trained model to some applications for science discovery or medicine or supporting our everyday life. So then the second topic is collaborative AI. So in particular, as a long-term goal, we'd like to realize co-evolution of AI and human. This is a main topic of today's talk. So here we show the current machine learning system and human intelligence. So we have 2 different intelligence in our world now. And between them, there is very narrow information channel so far. Human can tell the label to the AI, and AI returns output value prediction or some classification result to human. Very narrow information channel. So we'd like to expand the channel. So for example, explanation or demonstration. And so then machine learning can use human expert knowledge, and also human expert can understand the output of machine learning system. And in addition, so both systems can use accumulated knowledge in a society or accumulated data in a society, and both systems can contribute to the accumulated knowledge to increase knowledge in our society, to believe the knowledge. So this is an ideal image of the research on the coevolution of AI and humans. And I'd like to introduce some examples of research in that direction. The first one is application to the in the medical image area. So the interpretability is very important in medical applications. And so we constructed two neural networks. First one is diagnosis network, and second one is a visualization network. Diagnosis network is, as usual, extract some feature vectors from the pathological image. And the task is a diagnosis of medical diagnosis of pathological image, assisting medical diagnosis of pathological images. And diagnosis network extract feature vectors, and we quantize the feature vectors to a quantized feature map. And using this quantized feature map, we make the classification with a very simple, interpretable classifier. And not only the diagnosis network, we also construct a visualization network. This network generates image patch from the dictionary index, and so making a CNN feature, extracted feature, interpretable for human doctor. And so combining these networks, we can construct a feature dictionary for medical diagnosis. And using this feature dictionary, the network can make the diagnosis, and also the human doctor can understand the reason of the output of the AI diagnosis network system, neural networks. And also, human doctor can point out some error or misunderstanding of the AI also. So both AI and human can improve the feature dictionary through the via collaboration by collaboration. And the proposed method outperformed existing explainable CNNs and achieved comparable performance with black box method like inception network. So the system can provide not only important area in the image as heat map. This is a usual information presentation method in explainable AI. but also the image patches correspond to the important area, so the doctor can understand the reason of the diagnosis, and also doctor can correct some wrong features in the dictionary. So human and AI can collaborate through the diagnosis, the dictionary with images. And in other research, we introduce the scientific knowledge of quantum chemophysics into a deep neural network. So that here the task is not a vision task, but predict a chemical property of a molecule. And this is a very important task to accelerate for finding the candidate chemicals for drug or catalyst or materials, as you know. And the research is now very active in this area. And this figure shows how quantum chemophysics knowledge and DNA are combined into one network. Around here is based on the knowledge of quantum chemophysics called linear combination of atomic orbitals approximation, LCAO method. This is established in a quantum chemophysics area and very popular method for getting the molecular orbitals from the molecular input data. Input is a coordinate of atoms in 3D coordinate of atoms in the molecule. And this molecular orbitals is equivalent to electron density in this molecule. So like this one. So this color shows the density of electron in the molecule. And these are very meaningful and important information in quantum physics. And from this information, we can predict the chemical property of the molecule using training the deep neural network as usual. So the point of here is we don't need to grant truth for this intermediate information. So we prepare just the input molecule information and the property of the molecule, a value, energy value, for example, and using by the end-to-end training of the whole network, we can get this very meaningful intermediate information representation automatically. So the effectiveness of introducing this kind of meaningful scientific grounded latent representation is not only training makes efficiently, but also extrapolation of the learning is an important effect. So usual machine learning can only make interpolation, as you know. However, this graph shows that our model trained with this small molecule with a small number of atoms can apply to larger molecule also. So this axis shows the error, mean absolute error. So the low error is better. But
네네네.
if you use a conventional graph neural network, the graph neural network cannot extrapolate to the larger molecules. So I think we think this kind of extrapolation is very important for real-world applications. So then I to move to the future direction of the research. So I'm myself very much interested in creating AI which can communicate with humans through natural language. So this is an ultimate goal of AI research. And there are several research topics towards this direction, such as image video captioning, video question answering, and video storytelling, and so on. And this is research in ARC in that direction. And we generate stories that are both diverse and informative for an input image sequence using common sense knowledge, the concept net. This is a big knowledge graph representing common sense knowledge. So from image sequence, we extract features and concept, detect some concept. And from the detection, we retrieve the knowledge, related knowledge in the concept net, large knowledge graph. And we select some important concept and we generate the story based on the selected concept. And these are two examples of our generated stories by the system. You can see that our system can generate more informative stories than the state-of-the-art system. And this kind of research direction is also related to the two information processing systems in human intelligence. System 1.
거기 있는 거 저녁에 다 썼지.
So as you may hear about
나 어제 저녁에 다 썼잖아.
this hypothesis, many researchers told that we have two kinds of information processing systems. System 1 is unconscious pattern information processing, and system 2 is a conscious symbolic information processing. And we humans can use both of systems very flexibly. So system 1 is very fast and unconscious and reactive and implicit and interpolative and emulation and non-verbal. System 2 is slow and conscious derivative, explicit and extracamp extrapolation and simulation with knowledge and verbal linguistics.
그럴 것 같은데.
In the research of AI, there are two different research streams corresponding to the two information processing systems. So the below here is a data-driven pattern recognition AI corresponding to the system 2, mainly based on machine learning techniques. And above is a knowledge-based symbolic processing AI corresponding to the system 2. So now deep learning appeared in this data-driven pattern recognition AI and appear from data-driven pattern recognition AI, and I hope it can integrate, combine the both research stream in AI. So to fill the gap between the two systems is a very important future research in AI, I think. So actually, many researchers started to do research in this direction. So this is from this picture is from the invited talk of Professor Yoshua Benzio in NeurIPS 2019 keynote speech, keynote talk. And he stated that current deep learning is a system 1 deep learning in fast and unconscious, and future deep learning is system 2 deep learning, slow and sequential unconscious. So I think the future deep learning should combine these two aspects of human information processing. And in other words, such system should use or treat causal knowledge behind the observable real world, observation of real world. So behind the observation of real world, there are causal structure represented like this graph, causal graph. So causal representation, the research on causal representation learning is aiming to extract embedded information representation reflecting this kind of causal structure behind latent causal structure, and utilize the representation to various downstream tasks. And some researchers are constructing data set, for example, causal video QA data set. And in this data set, there are movies of the collision event of some objects. And the system should answer very complicated question about the video. So I hope the research in this direction will success to realize the core evolution of human and AI. So this is a summary of my talk today. So AI in internet service is the first stage, and now we are trying to implement AI into various learning services. AI system R&D in this direction, and they visualize computational resources. And we are compiling data sets, models, and algorithms, promoting explainable interface with collaborative AI, behind AI, and physical AI. And co-evolution of AI and humans is an important direction of future research. And I hope as an AI researcher, more research will be conducted by collaboration of vision researchers and many researchers in the future. So these are the characteristics of our research presented today. And thank you very much for your attention. I also thank to NEDO and JSPS for supporting our R&D activities. So that's all. Thank you very much.
Thank you very much, Mr. Hideki. Very interesting and informative talk. I was very impressed. We have a very short time remaining. From the attendant, is there any comment or question? If you have any question, please push the button, raise a hand.
Can I?
Yes, please.
Yeah. Thank you so much, Mr. Asa Sensei. It was very fantastic for us too, especially for your big infrastructure like ABCI. I'm very fascinated with that kind of concept because that has been very, very big size work platform or as an infrastructure. You mentioned that not only NICE, there is a group from the Sony team has been collaborated to build that infrastructure. So I'm not so sure how much they have been used for general researcher or ordinary people can access to that infrastructure to use that.
So unfortunately, I'm not sure for overseas researchers, but for Japanese researchers, we provide
Okay, I see. So
facility.
that is wide open for Japanese researchers.
Yeah.
Domestic
Even in private companies.
Okay.
Yeah.
Very fantastic. Thank you so much. We also in Korea we have many attempts to build up the infrastructures, especially for building up building up the data sets we have by the national governmental site with an agency. So, but we don't have such a big infrastructure for general users.
Yeah.
So infrastructure was very, very fantastic for me too. Thank you.
Thank you very much.
Is there any other questions? Okay. Okay. Lastly, I want to ask one question.
Yeah.
For co-evolution of AI and human, we need some representation which share the AI and human.
Yeah.
Usually, scientific knowledge is written in mathematical equation.
Yeah.
And do you have any suggestion or idea how to represent the knowledge?
Yeah, it's a very interesting question, and I have no answer. But maybe I hope because our human can understand the language and the mathematical formula. So I hope the knowledge is represented in such kind of language or formula. And so AI should understand the language for mathematical formula.
Oh, okay.
I think.
Okay, thank you very much. Thank you for the interesting talk. I want to close this keynote lecture session. And next, the oral